Okay, welcome to Complexity Made Simple and the latest tutorial. This tutorial, which again is with DOE Pro, today we're going to look at how to analyze historical data. So I've got a little example. I suppose the first thing to say before we do this is quite a rare thing for me to do. I only have one example where this works. You're going to see a little bit why that might be the case in a moment. But often you've got lots of data about you, maybe years and years of production data and things like that, inputs and the output responses, and you may want to analyze them. So I'm going to show you how to do it. The first thing to say before we get into the actual analysis itself using the software is how to prepare the data. So the little example I have, we have a motor. We are measuring the decibel level, so dBA. So this is the response here. We're measuring noise coming out of a motor after it's been assembled into a pump. So actually the noise is coming out of the pump assembly. We've done some component swapping that shows us that the motor has a huge influence on the noise. And then I literally have thousands and thousands of records, and I have thousands and thousands of motors where I can analyze some of the features. So of course the first thing to say is, because the motors are built, I don't have control over the inputs. I cannot do a proper DOE because I cannot manipulate the inputs in a pattern. All I can do is measure the inputs, measure the output, and then analyze the historical data. So that's the way that I'm going to look at this, rather than creating an orthogonal pattern as we normally would do in a designed experiment. So as I say, the first thing to say is, you'll notice, look, I mean, I've only got 19 data points. Actually, when we did this, we actually started off with 20. One got lost during the tests that we were doing, so we ended up with 19. But the 20 tests that we chose, the 20 motors that we chose to test, what we basically did with them was we split them in half. And low, for me, by the way, low results is good. They're the best. And the bottom here is the worst. So what I've basically done is I've used one of Shannon's techniques, where we have selected, I sorted all the results. So I had thousands of data points. I'm not going to try and analyze thousands of data points. What I'm going to do is I'm going to analyze the big signal. So in order to put a big signal in the data, I've put the data in order as far as the output is concerned. And then what I did was I selected the top 10 and I selected the bottom 10. In other words, the best of the best versus the worst of the worst. So what I'm doing is I'm putting a big signal into the data set, as much as I possibly can anyway. So if I put big signals in the output, I should see if these inputs are linked to the output. I should see big signals in the input to output link, essentially. So that's the first thing to say. You do not want to take thousands and thousands of data points and try and analyze it. All you will do is put huge amounts of noise into your data set and probably not see anything at all. So use one of Shannon's great techniques, Bob versus Well. Okay, so that's the first thing to say. So there's the data. I guess the other thing to say is that when we did this, these were the three inputs that remained after some pre-analysis. So we did a simple scatter diagram analysis where we did simple regression, y equals mx plus c. Got a nice r squared value for the inputs to the output. These are the only three inputs that came up with any kind of decent r squared when we did that. So now I'm going to do multiple regression on these three. So that's the other thing to say. These three inputs were not the only three. So we've prepped the data before we've done this analysis. We've cut down the number of data points by going Bob versus wow. Then what I've done is if I put huge signals into the output, if the inputs cannot relate to the output, despite the fact that I've removed enormous amounts of noise from the data set, it's very unlikely that they have a link to the output. These are the only three that remained, and these are the three that I'm going to analyze therefore. Okay, so I have to set that up first. So let me go to Excel. So I'll come out of this. We'll go to Excel and we'll have a look at this data set. There it is, sitting in an Excel spreadsheet for us. Now what we have to do, of course, is go and use Sigma Zone. But instead of going create design, which is what we would normally do, and the computer tell us what the pattern is, we're going to go to the next one across, which is historical custom designs. And the first thing it says is create a design matrix. So I'm going to click on that, and it says, okay, how many factors do you have? How many inputs? Of course, I have 3. And how many runs do I have? Well, I've got 19 rather than 20. Click finish. And then look, I get this empty space that's waiting for my data set. Now what I can do, I can copy and paste this across. Of course, you could just type it in if you wanted to. So if it was on a pad and you wanted to type it in, then you can do that as well. I'm going to copy it in. You'll notice that I also copied the names of the variables in as well. So that helps the software, and it will name them when I do the analysis. So go back to Sigma Zone, back to historical data. Now it says interactions, coding, and replicates. So the first thing is, how many interactions do you want? How deep do you want to go? Now, I can obviously ask for the 2-way, and I could ask for the 3-way. But I'm not going to be greedy. My advice here is not to be greedy on the analysis. Don't go too deep on the analysis. So I only ask for 2 ways normally when I do this. Then it says, how would you like to code the columns? Obviously, normally a DOE wants to be coded. That's the way the computer wants to work. Because I've just give it a pattern, it doesn't know the coding. So what it will do is if I auto code, it will look into the column, it will pick the biggest number, call it +1, it'll take them up the smallest number, call it -1, and it'll give the others a coding value on the same scale, if you like. So it will prorata all the coding. That's what I like to do. Auto code is the choice I always make. Then it says, how many responses do you have? Well, I'm only measuring one thing, and in this case, it's decibels. And finally, how many replications? How many repeats of each setting do you have? Now, because this is historical data, and often they've been tested randomly, often you don't have repeats, and I don't have repeats in this case. I just have one repeat. And of course, what that means, I cannot analyze for standard deviation. And then finally, name the output, and it's called DBA. So there it is. Now it's waiting for the results, of course. So I'll go to my original data table. Let's get the numbers. Again, just copy and paste them across. You could just type them in if that's what you've got. You've got them on a piece of paper and you want to just type them in. So there we go. You'll notice, look, that there's some C's at the bottom here. The C's basically are there to tell you that the computer knows that the pattern is coded. So the computer is happy with this because it wants to work in the coded world. So it's ready to go. So now I'm going to analyze this pattern as I normally would, which is the first thing is to do a marginal means plot. And there it goes. Of course, it only gives me the 1 just for the Y hat. It doesn't give me the S hat marginal means. So, okay, what do we think of that? It's a little bit unusual. But if we look here, oops, I'm going to do that then, stop that a second. If we look here on the amps, this side, look at the link there, that's a very strong link. Now the other ones, look, there is a little bit of a sense that maybe that's going up that way, and there is a sense that maybe that's going up that way. One of the things you've got to bear in mind with this type of analysis, this pattern is not orthogonal, and therefore you are not going to see typically clean signals like the amps on the end. You're going to see this kind of rough signal, maybe some flyers sticking out there. That's typical of when you do historic data analysis, I'm afraid. So let's go back to the design sheet. Go back to Sigma Zone, and then we're going to analyze design again. Now, having done the graphs, let's do regression. Okay, let's blow this up a little bit. So here we go. Let's have a look. We've only got the Y model on the left hand side. So we'll just make this a bit bigger. There we go. So I can see that. So a couple of things before we do any analysis. First of all, look at the R squared. Really good R squared, 0.87. That is probably down to the fact that I've picked Bob versus wow. So, you know, I've driven a big signal in there. There's lots of signal, not so much noise. So that's a good sign. I've got some nice red p-values, which of course is saying that the amps, the revs and the throw seem to be significantly linked to the decibel level. So that's good as well, and that's what I would normally look at. But because this is historical data, we have to look at some other numbers, and the first thing we have to look at are these tolerances. Now the tolerances tell you how orthogonal the DOE pattern that you've analysed is. And the tolerance column is very important when you're analysing historic data. When you do a normal orthogonal DOE, the tolerance will say 1 in all those columns, in all those cells. 1 means 100% independent. In other words, this coefficient here, look, 2.556, would be, if it said 1 in there, 100% independent of all the other, coefficients here. So that would be 100% independent. It isn't. Look, it is 45% independent. In other words, we have some confounding going on. Some signal is coming from somewhere else in the pattern. So that 2556 is not independent. Okay, so see the next one down, look, is pretty good. 89%, 0.89, 89% of that coefficient is clean. It genuinely belongs to the revs per minute. So looking at these tolerances, they're not bad actually. We would want to get to 0.5 as a minimum. So we want to get 50% clean if we possibly can. Obviously any number above 0.5 heading towards 1 is where we want to go. But at the moment, these are pretty good. Often when you open historical data files and you do this, these tolerances are terrible. They are down at 0.01, 0.1, and they never recover. So this is actually pretty good. I'm quite pleased with this. Now we're going to regress the model as we normally would do. So I'm going to take the A-B interaction out first of all, delete the X, Sigma Zone, Analyze Design, Regression. Let's see what happens when we do that. Let's blow this back up, look. So there we go. I've taken the A-B interaction away. What's immediately happened? Look, the tolerance for A has gone up now to 0.89. That's 89% clean. That's really good. Now the reason for that, the A-B interaction was badly aliased with A. That is often the case. Variables often get aliased quite badly with their own interactions. And in this case, the A-B interaction was very badly aliased with A. Now that I've got rid of it, that's no longer the case. So this is looking quite good. Let's take the next one. Let's take the BC away. Let's see what happens there. So away goes BC. Marginal means, there we go, multiple response regression. Let's blow it back up. And what are we seeing? Same thing, look. Now the tolerances are beginning to look great. We've got, you know, at the worst case, look, red p-value on the throw. The throw tolerance 0.62. That's pretty good. You'd go with that. You'd use that. So finally, I'm going to take the AC interaction away. Let's see what happens then. Okay, look now. Now look at that. All of the tolerances are in the 90s. And I have to say, this is a very lucky day at the office. Um, I've done lots of historical data analysis, and the tolerances have nearly always been terrible, and they've never recovered. Whatever I've tried to do, they've never recovered from, let's say, above 10%, zero point 0.1, which is awful. In other words, only 10% of the coefficient is coming from the main effect. Now what we have is good red p-values here. I have great tolerances. I've still got a good R squared. Look, you'll notice the R squared went down from 0.87 to 0.85. As you take terms out of a model, the R squared always does go down. But even so, 0.85 is great. And these coefficients actually are very practical. If you know anything about decibels, 3 decibels doubles the noise energy. So if I total this up, look, what have I got? I've got nearly 3, 5, I got sort of 6 decibels with these 3 variables. That's a massive movement in terms of noise energy. So this is looking really good. This was a good historical data analysis. Now, of course, what I've got to do is prove that the model works. So the next thing to do is to go back to my pile of data. So the thousands of data points that you have. Now what you can do is you can select some of those data points. So maybe you pick up one and it's got an amps of 1.15. You just type it in. It's got a revs per minute of, let's think of a number here, 88.6. Okay, dial that in. And the throw is 1.44. That's the one that you've just picked up. This would be one of the thousands of data points that you rejected. If you now scroll down a little bit, it says, well, if you put this on test, I'm expecting a decibel level of 47.58. And of course, what you do now is you go and you test it. And if you get close to that, it's actually saying that I should be in these boundaries here, but you'd want to be closer than that. 47.58. If you get close to that, then try it again with some other unit. Try it again. If you get close results, this model is working. I mean, don't forget, 85% of all the movement in the numbers is due to these variables. So the likelihood is you're going to get pretty close to this. And that's the way to use historical data analysis. It is a rare thing to do. It is a rare thing to do because normally it's badly aliased, and therefore these tolerances are nearly always poor. But if you have a lucky day at the office like I did in this case, and you have no other way of doing the analysis, then historical data analysis is possible in DOE Pro.